Welcome! Here we have a Heathkit H-8 computer made by the Heathkit company. This has long been on my list of things I wished I had in my collection, something I've always wanted to play with, build expansion cards for, upgrade, etc. ever since I saw it in the Heathkit catalogs back in the late 70s or the early 80s. These were quite popular in their time. This one here I just got. It's a very bare bones one. I'm going to do a series of videos on upgrading it, both with cards that other people have designed as well as cards that I will design. Okay, I've got something new here. Shall we open it up and see what it is? That is a Heathkit H-8. My friend Glenn on the SEBHC forum, he managed to set me up with this one for a really good price. It's in need of a little bit of work maybe. Missing the lid, got a chunk of wood there. We can work on that. Get the inside, we've got lots of bubble pack here. Goodies inside. We've got over here in this bag, what has Glenn sent me? I believe it's a memory board. H-864-2 memory board, so this should be able to get us going with some RAM. And this is an unbuilt H-8 or HA8-1. This would be the Zero Org board. So we've got some goodies there. Alright. Okay, let's take a look at this H-8 computer. This is what you'd think is a fairly bare bones one. Doesn't have a lot of boards in it, and the boards are pretty basic. It has the 8080 CPU board, this one here. It has the H-8-5-2 serial and tape board, which is back here, and it has the FP2 front panel board. So these things, the backplane mounts to the side. I've never had another computer that was like that, where these things plug in sideways. But hey, it's Heathkit, and it worked for them, and obviously the computer was quite popular. So these things actually screw in from the bottom. You have to like flip the case on its side and unscrew them. I've already pulled the screws, so we can just unplug a board. Take out this tape board. Take out this, whoops, this one actually, there's a cable in here that goes to the front panel. Watch out for that. There we go. Okay, here is the CPU board. Not a whole lot to see here. We have the 8080A genuine Intel CPU there. We have over here, we have a ROM. This is the 444-13 ROM, which would be the PAM8 panel monitor for the H8 is what would be in that ROM. It's pretty much the first ROM that these came out with. And then this here is this an 8238, some kind of support chip that goes with the 8080. We've got a little bit of logic around. Like I say, a relatively straightforward board. There is a voltage regulator over here on the side, mounted via these wires into this board here, which makes a heatsink for it. Okay, and here is the tape and serial board. It has two 8251 asynchronous serial receiver transmitters. This one here is for the tape interface, this one here is for the serial port. The serial port is here, this would be your console port. Did not come with a cable, but I have already made up my own cable to a DB9. Plug that in there, go out the back of the case, and be able to talk to this thing. The tape interface has a couple of RCA jacks there and there for in and out, as well as a header down here which hooks up to these relays and can be used to turn your tape on and off. It can interface with two tape players, one for record, one for playback, two separate relays, or the way this one is jumpered across, they're actually tied in common, and you can use one tape player for both play and record. Again, we have a regulator over here on the side bracket. A lot of analog circuitry over here with a couple potentiometers that have to be calibrated properly for your tape board to function right. Okay, so let's power it up, see what happens. Powered up, we've got run and power, but no monitor light. And the keypad doesn't do anything. And I think the reason it's not doing anything is because I haven't installed the RAM board yet. So we'll shut it down. I will insert the RAM board, and we'll see if it comes up this time. And you do always want to be careful plugging these in. Make sure you're not like off by one. Some of the boards are keyed, so you can only plug them in one way. Turn it on, and it has started up. So it is displaying some memory address, but you can easily go through memory here. So let's mem 040100. We can see that byte 153 is there. You can move up and down. If you push the alter button, let's change 153 to a 201, and then it has moved to the next address. So let's go back to memory mode, and there at 040100 is our 201. So we seem to be able to read and write memory with this thing. Next up, I think we will want to try out the tape controller and see if we can load a program onto it. Now, if I actually had physical cassettes, I could put them in my tape player, I could play them, but I don't actually have physical cassettes. What I do have is an image of Benton Harbor Basic from the internet, which I have converted to a WAV file using a program called KCS, that stands for Kansas City Standard. So what we will do is we will turn this on and we will play that WAV file to it. Now, I initially tried using my Windows laptop to do that. That did not work very well. It would not recognize that at all. My suspicion is the Windows laptop does something to the sound that it emits, which is messing with it in some way that the computer will not interpret it. So what I have done instead is I have hooked up a wire here, comes out, hooks up to a Raspberry Pi, and we're plugged here into the 3.5 millimeter audio out jack on the Raspberry Pi. So let me turn on the H-8, push the load button, and I will go over here and run a play. Okay, and as we can see, it has started to count, and what it's doing is displaying the memory address it's writing and the value it's writing. Keep in mind these addresses and values are in octal. It's going to count up till it gets somewhere close to 80 octal, and that'll be the end of the Benton Harbor Basic program. Now that continuous beeping is not good. That implies that what had happened is it had an error, and the 001 tells us that was a checksum error. So somewhere in here some byte is wrong. So if we went through memory and we went 040100, we can step through memory, and I've actually done this a little bit when I had some errors, and we could compare it to the sheet and see which byte is wrong. And yes, somewhere in there is a wrong byte. Now here is the RAM board that Glenn sent me with the computer. It was an aftermarket board. It's the H-8 64-2. Now Glenn told me when he sent this to me that he wasn't sure this board is reliable with the 8080 board that came in the H-8. Said he kind of got it to work, but he thought there were some glitches. So I may take and replace that with this board here, which is the H-8 64K RAM 8080A Z80 ORG0 board. So this is going to integrate a new feature called ORG0 that will let you use CPM, as well as it has some dip switches to switch each bank of RAM on and off in 8K chunks. So we'll try building this one up and see if we have any better luck with it, with that issues we were seeing with the tape loader. So I'm wondering if the tape loader problems could have not been tape problems, or problems with the tape loader board, but problems writing to memory. So we'll give this board a build out. We'll see what happens. This one was developed by Norberto. This is revision 1.3 from 2017. Okay, here is my newly created memory board. You can see, compared to the other one, it's quite a bit bigger because it's got a little bit more stuff on it. It's got this big prototyping area. But this is both a memory board and a zero org board. So it does have an AS6C 1008, that's like a 1 megabit or 128 kilobyte chip. But it's also got on here bank selects where we can turn on and off parts of it in 8K segments, turn any part on or off. The reason Norberto suggested I do this board is so that we can turn off the first 0 to 8K. Thinks that might give me more stability. It's also got a status port down here that's used to configure the XCon 8 monitor. We're not running that. I'm running the old PAM monitor, so we're not using the status port yet. That'll come into play later when we want to do CPM and org0. Also has some stuff to do multi-sides on the H-17 disk drive. Also not using that. It's got the ability here to put battery backup for your RAM. I don't have a battery, so I did not implement that. I used a modern switching regulator over here for the 5 volt. The real ability we're getting with this board over the other one is to turn off this first 0 to 8K and see if that affects the tape behavior to see if it's any more reliable. Okay, I did install this board, and unfortunately it is no more reliable in my computer when using the tape drive to load tape programs. So whatever problem I'm having, it's not related to the RAM. It's related to something else on the tape board itself. Okay, the tape audio has been problematic, and I'm trying to get a reliable way to load tape programs so that I can do my demo. And what I'm going to do is I'm going to inject directly into the tape's UART. So this thing has 2 serial ports. One of them comes out here and goes up here to the console port. The other one goes to all this tape circuitry and is where the tape comes in. So the audio comes in here, there's a phase lock loop, there's some other stuff, there's all kinds of analog processing, a space detector. It has to go through all of that to get into this UART. But what we could do is we could grab pin 3 of the UART. It's this one that comes down right here on the top, comes on over here and goes into this chip. We could cut this and we could inject the serial directly into this UART, and that would allow us to bypass all of the audio processing. We could just blast the program right into there and hopefully be rid of our errors. So what I did is, rather than modify the board, at least that was my thought when I started this, is I would pull the UART out and I would build this piggyback board. So this piggyback board, all it does, piggybacks all of the pins except pin number 3, which I ran out to a 100 ohm resistor and ran to this little header here for FTDI. And then all the other pins hook straight through, so we can take our UART. So we just take our UART, plug them into the piggyback board. Then we can very carefully plug the piggyback board back into here. And there we have it. And now we can just take any FTDI cable, your standard TTL USB cable like this one here, plug it into here, plug this into the laptop, and we'll be able to blast our programs directly into that UART, bypassing any analog funny business that's going on over there. Okay, let's try this again, but this time we're going to send the program digitally rather than using audio. So I have an FTDI cable hooked up to my little piggyback board on the tape adapter, hooked up to the laptop, and then I have a separate USB serial hooked up to the serial port, hooked up to the laptop. So we've got 2 screens available on the laptop. One of them is going to be to send the program data to the tape port. The other one will be to send and receive the serial data from the computer. So as usual, I'll push the load button, and then I will initiate a file transfer. This is my favorite terminal program here. We'll just do send binary bhbasic1.h8t. And there it goes. You can see it counting along, and this time we will get a flawless program load. Okay, so all I have to do now is push the go button. The program counter's already loaded to the right spot. And Benton Harbor Basic has loaded on the laptop. Now it seems to have another prompt here with this dot. The normal prompt is an asterisk. I don't know what the dot prompt means, but we'll just hit return. Yeah, see, now we've got the asterisk, which is Benton Harbor Basic is ready to go. So let's do a quick program, 10. Now you'll notice it does completion. So I hit PR and it automatically did print. I find that kind of annoying. go to 10. And then we can hit RU. Whoops, I hit RUN, so I got an additional character, but we'll backspace over that. And there we go. So good, we were able to load a tape program to the tape board, even though we did it digitally, and now we're able to run the program. We've got Benton Harbor Basic working. Okay, next up, let's build a speech synthesizer. A speech synthesizer is usually one of the very first things I build with any vintage computer. I built half a dozen of them for half a dozen different computers. So let's build one for the H-8. We will design this board to use the popular Votrax SCO1A or the much more popular, much more available SPO256A-AL2. So let's get started with the H-8 bus. So I've got it down here. Right here. So it is a 50-pin bus. They usually break it out into two connectors with a space in between. Starting at this connector, we've got a ground. We've got some power. So there's a minus 18 volts here, a plus 18, and a plus 8 volt. You'll notice there is no 5 volt. You are expected to put a regulator on every board. Now, some of the people building the new H-8 2000s, they will use an ATX power supply, and they will just supply 5 volts, and then they will strap the regulator across. But for vintage accuracy, it would be this 8 volts and then regulated on board. You have some pins here for interrupts, no surprise there. But then you get to the data bus, and things are a little bit unusual. You have D0 through D7, and these are inverted data bus signals. So they ran them through a bus inverter, and you'll need to put another bus inverter on your expansion card to invert them back. You've got the M1 signal, which is for the M1 cycle of the CPU. I don't actually remember what ready in is. It could be due to wait states. I would have to double check that one. But we have IO write and IO read, which the computer will strobe when you're doing a read or write access. You have this O2, which is a clock, memory write and memory read for memory accesses. 19 and 25, those could be grounds or those could be user-defined pins. That depends. Then over here, we have a whole bunch of address bits, 16 address bits. We have a ROM disable pin. This will disable the ROM on the CPU board. This would let you either go with an external ROM, or it would let you run in something called org0 mode, which I will cover in a future video. Last but not least, we've got a few more little bus signals. We've got reset, we've got hold and hold A. These ones are like a bus acquisition thing. You can assert this one, wait for this one to come up, and then you can grab the bus. We've done very similar things on the Z80. I think that covers the whole bus. It's relatively simple, pretty easy to interface with. So let's see, what are we going to need to do? Starting over here, we need to do addressing. We need to take our speech synthesizer, we need to put it on a port. Sometimes I will do that inside of ATF16V8 PLD. Other times I will use a circuit similar to this with a 74HCT688N comparator, which what it basically does is it compares the bits on this port, and it asserts this signal if they match. So you put a bank of dip switches here, and then you can set an address on these dip switches. And then finally, I've got another jumper down here that is a board enable jumper. You do not install this jumper, this signal here will be pulled high, and we will not decode anything. That's easy just if you want to disable your board, one jumper rather than having to pull the board. We've also got to do a little bit of work down here decoding some bus signals. So I did combine a bunch of junk into one ATF16V8. And a couple of things that I've done is take in the IO read and IO write signals, which are actually active high, and combine them with the IO cell, which is the one that came from up here. And then we can output signals here, this ALD and strobe, to our speech synthesizer chips in order to cause them to load a phoneme into the speech synthesizer. That's the first function I implemented in this PLD. The other function is I implemented some open collector status outputs to the data bus. Now a lot of people don't know this, but an ATF16V8 can be put into high impedance. So you can put these in high impedance where they are not loading the data bus at all. And you can use them to implement yourself a read port. So there will be some status that comes here off the speech synthesizers. And when we do a read on this chip, we can actually put that status out on the data bus. And we can do our little inversion trick there with having to invert those signals. So that's a bunch of glue that we stuck in that PLD. And of course, I'll put the PLD signals up on my website. Now let's go through the Votrax SCO2A. And it is here. So remember, we've got those bus signals are inverted. So we need to re-invert them back. And I did that here inside of this latch. This is a 74 HCT 533 inverting latch. So whatever comes in this side is inverted going out that side. And the reason why I chose to use a latch instead of a buffer is because the Votrax has these inflection pins, this I1 and I2. These things are not latched into the Votrax itself. They're live all the time. So we need to latch what the user program wants and use it to apply these signals to the inflection pins. Now, the other thing about these inflection pins is they're actually driven by 12 volt rather than 5 volt. The Votrax is a weird chip. So you've got these little driver sections down here, which take the value of the latch and put it in there in the inflection pins. Now, the data bus to select the phoneme is up here, these 6 pins. That just goes straight through the latch. Doesn't matter that we latch it. We'll still load it here via this strobe pin. I listed this as option 2. We described it first because this is where the latch is. But our other option, option 1, is the cheap option. So Votrax is very expensive. They can run you like 100, maybe 200 bucks. SPO 256, A-AL2, maybe 15, maybe 20 bucks, maybe even less than that, and very plentiful on eBay. So it doesn't sound quite as good because it does not have those inflection pins, but it's still a pretty good speech synthesizer, and you'd find this used in your TRS-80 Coco, speech sound pack, stuff like that. So interfacing it is not a whole lot different. We have a bunch of pins that will select the phoneme, and I hooked those up to this latch, just like we did with the Votrax. The Votrax had 6. We've got 8 of them up here, so we'll use all 8 pins down there on the latch. And then you have ALD, that is your strobe to load the phoneme into the speech synthesizer and start speaking. Out of it comes an SBY, standby, and LRQ, load request. Load request is the one that will go low when the speech synthesizer is ready for a new phoneme. Now, coming out of either one of these speech synthesizers, and by the way, only hook up one of these, don't populate them both, was not designed to do both, is a speech pin. So here it comes out here, here it comes out here. This is a digital that you'll need to do a little bit of filtering on to turn it into decent speech. And what I do is this is something that I have added to my designs lately is this active filter. Sometimes they just use a passive filter. I've come up with an active op-amp filter, selected some values in here to do a little bit of low pass and high pass filtering to filter out the audio of that speech synthesizer, because otherwise it will be extremely kind of like buzzy if you don't do any filtering. So got the op-amp filter. Then we go into an LM386, the LM386 being an audio amplifier. I put 2 different jacks on the board for the audio output, depending on which is more convenient, side exit or top exit, and also a jack down here for line out. Here we've got a volume control. The last thing to discuss here is the power filtering. So the 8 volt comes in from the H-8. You put it through a filter capacitor into a regulator. Got some capacitance on the outside of it. Then I think I got this 10 ohm resistor from one of the Votrax schematics. I think this is just doing a little bit of extra filtering where you go into a few more capacitors. You could probably switch that out and put an inductor in if you wanted to, but back in the day, they must have used resistors. That is sufficient for your SPO 256. For your Votrax, if you decided you needed to go that option, you would also need a 12 volt supply. So here we've got another regulator footprint for 12 volt. 18 comes in, 12 comes out. Put a fuse on there because the Votrax is an expensive chip. You don't want to accidentally screw something up. Better to blow a fuse than blow a $200 unobtainable IC. And, then we go out here to the Votrax. Okay, here is my speech synthesizer board. Finished up and ready to test. So we've got the big header here. It's actually 2 headers. I did not use the fancy, period accurate, expensive headers. I used some very cheap ones off of eBay. I did glue in a piece of plastic in the middle there because you always want to key these so you can't get them off by one. So you block out one pin between the 2 headers. Here's the SPO 256 speech synthesizer chip. Over here we have the ATF 16V8. We have the 74 HCT 533. And then up here we have the 74 HCT 688 together with its dip switch and pull-ups. We have a very tiny, this is a Pololu regulator here, which will regulate the 5 volt. And it's a buck boost converter that will actually work at 5 volt. I mean, it can be 5 volts in and 5 volts out, which is kind of nice if we ever upgrade this to use an ATX power supply. But it'll also take the 8 volts that come in off of the vintage Heathkit and convert it down to 5. Here we have the LM386, I think is that one. The op amp, LM358 is that one. You've got the crystal here that goes with the speech synthesizer, volume pot up there in the corner. And a couple of jacks for audio out and speaker. Another footprint here if I wanted to put the speaker at the top. All of the Votrax SC01 parts I have left unpopulated. I'm not going to do Votrax in this video. One of these days I will come up and revisit that. And there's also jumpers here for interrupts if we wanted to make this interrupt driven. Okay, let's test out our speech synthesizer. The nice thing is that since this computer has a front panel, we can actually try it from the front panel. So I put it at address 74 octal, so let's go memory. We'll write, how about an 012074. So that's one particular phoneme. Different phoneme. Yet another one. And that'll stop it. So the other thing we can do is we can input as well. So if I push the in button, we will see that right now there's a 5 being read on that port. And that indicates that 2 bits are on. The 1s bit, the lowest one, is actually the bit where the speech synthesizer is asking for a new phoneme. So we can both write phonemes out as well as read status back. Now I'm going to upload a program that will have some speech phonemes that we can try out and listen to the speech synthesizer. And we're just sending this as ASCII straight into the terminal, so it should enter this program. But I think I have corrected that line. Let's get rid of this dead one that it entered in. Now we can run it. Okay, sounded good. You can tell this program's been around a while. It's been through several of my other projects. Now you can hear it speaking kind of slowly. Okay, next I'm going to do Daisy Bell. This is not going to sound as good as the Votrax Daisy Bell that you've heard like on Hero Junior Robot, because that's Votrax. It does inflection levels, whereas SPO 256 does not. Here we go. And how about ABCs? Epson QX10. Okay, so it's obvious that the slow CPU, together with the basic interpreter, is drawing out the speech. I'm going to have to go back and I'm going to have to write an assembly language routine to do that and make it sound right. I'm not going to do that today for this video. That'll probably come in a subsequent video. We can revisit this next time maybe. Or we'll revisit it once we have the Z80 CPU board and it runs at 4 megahertz or better. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.